Quark-gluon plasma. What is that? And why is it so interesting? Well, to understand that, maybe let's go word by word. Let's start with plasma. So plasma is a state of matter, sometimes called the fourth state of matter after solid, liquid, and gas. So in general, as you add energy, for example heat, to a system, things don't want to stay together. We're used to the fact that if you heat up a solid, it'll become liquid in general, and if you heat up a liquid, it'll become a gas. Solid, liquid, or gas, but these are just different levels of freedom. A gas is just the molecules of a substance flying freely and occasionally colliding with each other. But what happens if you add more energy to a gas? Well, the temperature will increase and the molecules will be flying faster. But what if you heat them up more? At some point, the collisions between the molecules will be so violent that they will start breaking up atoms. Now, an atom is a nucleus surrounded by electrons. And given high enough temperature, the collisions between the atoms will start ripping electrons away from the nuclei. And you'll get a gas consisting of free electrons and ionized nuclei, which is what we call plasma. And you can see it anytime you look at lightning or the sun, for example. Quark-gluon plasma is when not only atoms, but the protons and the neutrons forming the atomic nuclei themselves break apart. Protons and neutrons are made out of particles called quarks, held together by particles called gluons. So it would be reasonable to expect that at some temperature, the protons and neutrons would break up and you will get a gas consisting of free quarks and free gluons. But here we encounter a problem. There's no such thing as a free quark or free gluon. And this is due to a peculiarity of the type of interaction that holds quarks together, which is what we call the strong interaction. So let's first maybe spend a moment on this. Strong interaction is one of the 4 currently known interaction types. Out of these, the 2 that we are most familiar with are gravity and electromagnetism. Gravity in our everyday lives is mainly responsible for things falling down, for planets orbiting around suns, shapes of galaxies, things of that sort. Electromagnetism is responsible for electric magnetic forces, for light, and many other things. Then we have weak interaction. The weak interaction is responsible for radioactive decays, and it plays a role in other nuclear reactions, for example, the nuclear fusion process that powers our sun. And the 4th type of interaction is the strong interaction. So the strong interaction is responsible for holding together quarks inside hadrons. Now, hadrons in general is the name that we give to particles made out of quarks, for example, the proton and the neutron. So the strong interaction holds together the quarks forming protons and neutrons, and it also holds together protons and neutrons inside the atomic nucleus. And out of the 4 interactions, the strong interaction is in several ways the strangest. One of its peculiarities goes by the name quark confinement. Quarks are confined inside hadrons and cannot exist freely. Now, to understand this, let's first take a step back for a moment and let's talk about potential energy. What is potential energy? Well, it's energy that's maybe not immediately visible, but it's just kind of sitting there waiting to be released, potentially. Now, without trying to do a full review here, let me just give you some examples. If I take an elastic band and stretch it, I'm accumulating potential energy in the deformation. And if I release it, this energy turns into kinetic energy. Now, I'm also accumulating potential energy here in the relative position of this elastic band and planet Earth. And I can release it by dropping the band. So let's stick with a familiar example. Gravitational potential energy. E equals mg h. Or how much energy is needed to lift an object by a height h, or how much energy will be released when the object falls back to the height it started from. So if I were to plot the energy versus height, so energy versus height, for example, height above the Earth's surface. So this is planet Earth here. If I were to plot this, I would get a straight line. Because as height increases, the energy increases linearly. But it won't be like this forever. This is just an approximation that works close to the Earth's surface, where our planet's gravity is essentially constant, where it doesn't change with height. But that's of course not true in general. Gravity weakens with distance. For example, if I could build a tower 2,500 meters tall, roughly, there's my tower, 2,500 kilometers tall. Earth's gravitational pull at the top of this tower would be about half of what it is on the surface. So over there, how much energy would I need in order to raise an object by a given height? Well, you guessed it, it's about half the amount of energy that I need on the surface. So the dependence on the top is like this. So basically the dependence of energy versus height looks like this in general. And in fact, the energy will never go above a certain value. Which means that if I give my object more kinetic energy than this value, it can escape Earth's gravitational pull entirely and go into space. All right, so let's go back to the strong interaction now. So here's the thing. The strong interaction does not go weaker with distance. As you move away, the force remains constant and potential energy just keeps growing linearly. Like this. Which means that you cannot free a quark, since the energy required to do that would have to be infinite. Okay, but even then, we should still be able to study a single quark by itself. For example, let's take a meson, which is a particle consisting of a quark and an antiquark. And let's take enough energy to separate the two quarks by some macroscopic distance so that we can look at each quark individually. Well, let's try. I happen to have a quark-antiquark pair right here. So what happens if I try to pull them apart? As I'm doing this, I'm accumulating potential energy in the system, and before I know it, I have two new mesons. So what happened? The potential energy in the system was so high that it was more than the energy corresponding to the mass of two new quarks, according to E equals mc squared. So it became simpler for nature to just have a quark and an antiquark pop into existence. So I had one meson, now I have two mesons, thanks to the energy that I put in. Quark-gluon plasma is a state of matter containing free quarks and free gluons. But we just said that you cannot free a quark. And it's true. Scientists have been trying for the past 50 years to free quarks from their confinement inside hadrons by smashing particles together at higher and higher energies and looking for free quarks, and never finding a single one. So how is it possible to have plasma with free quarks inside them? Well, you need to change the approach a little bit. Instead of trying to break up protons and neutrons to expose free quarks, we can take protons or neutrons and try squeezing them together. And at some point, the density of particles will be so high that you can no longer see where one ends and the other one begins. Everything will melt and form a soup of quarks and gluons all interacting with each other. And inside this soup, the quarks and the gluons are going to essentially be free. It's just that the density needed for something like this to happen is rather extreme. Bear in mind that the atomic nucleus is over 10,000 times smaller than the atom. So conditions in which matter is squeezed so much that not just atoms, but atomic nuclei are pressed together, such conditions pretty much only appear inside neutron stars, the densest objects in the universe. Now, this kind of density is not something that we can reproduce in the laboratory. So to study this state of matter, we change one more parameter besides density, and that's energy. When two protons collide in the LHC, energy changes into mass, and many new particles are produced, hundreds sometimes. So when two lead nuclei collide, we have about 400 protons and neutrons in the collision. You can imagine what's going to happen. Thousands of new particles are produced. They all interact with each other, producing even more new particles, and this pushes the density high enough for the plasma to form. Then, as it expands, it cools down, a phase transition occurs, and quarks form hadrons again. So this is quark-gluon plasma. A droplet of quark matter hotter than anything else in existence. About 10 microseconds after the Big Bang, all matter visible today was squeezed together into a sphere with a radius of about 50 kilometers. And at that point, the whole universe was in this state. Then it expanded, cooled down, hadrons formed, then nuclei, atoms, stars, galaxies, and finally, us. The universe went through several phase transitions in its earliest moments, but the transition from Quark-gluon plasma into hadrons is the only one that we can reproduce and study today. Quark-gluon plasma is also a fantastic laboratory for studying the strong interaction in detail. The strong interaction not only holds protons, neutrons, nuclei together, it's also responsible for most of the mass of everyday matter. It's not the Higgs field. The Higgs field gives masses to elementary particles like quarks and electrons, but protons and neutrons, the mass of the three quarks inside only accounts for about 1% of their masses. 99% of the mass of the proton comes from the kinetic energies of the quarks and gluons moving inside and from the complex interactions between them. We have a pretty good understanding of how this works, but not to the point where you can exactly calculate the mass. We really need to study the strong force more, and quark-gluon plasma is perfect for this. So, how do we produce such an exotic state of matter in the lab? And how can we study it? How hot is it exactly, and how do we measure that? All of this in episode 2.